Welcome back to this course on multi-core systems. In this lesson I will present an example cache coherence protocol, the MSI Write Invalidate protocol. Now that we established that Write Invalidate requires less bandwidth than Write Update and is therefore preferable, let's look at an example Write Invalidate protocol. For reasons that will become obvious in a second, it is called the MSI protocol. In this protocol, each cache block can be in one of three states. The first state is the invalid state. This means that the block is not present in the cache, or maybe it was present, but it was invalidated by a write from another processor. In any case, the block is not present, and in case the processor tries to access it, it will incur a cache miss and will need to fetch it either from memory or from another cache. The second state is the shared or S state. In this case, the block is present in one or more private caches, and therefore all these processors can read it without having to communicate. The third and final state is the modified, the M state. It means that the block is present in one cache only. Therefore, that processor can read or write it without communication, but if other processors try to access that block, they will need to get it from this cache. As a side note, the textbook calls the modified state exclusive, which in my opinion is somewhat confusing because there's another protocol called MSI where the E stands for exclusive. To avoid this confusion, I stick to the original name modified. I will now draw a number of state diagrams. In these state diagrams, there is an arrow from one state to another state if a certain event occurred that caused the state of the cache block to change. Furthermore, each arrow or state transition is labeled with up to 2 events or actions. The top label in normal letters is the event that caused the transition. The bottom label in bold letters is the reply to that event. On this slide, I will show the state diagrams for CPU requests such as reads and writes to a cache block. On the next slide, I will show the state diagram for bus requests. First, let's consider the case where the CPU tries to read an invalid block. This corresponds to a read miss since invalid means that the block is not present. This in turn means that the block has to be fetched from another cache or memory, which implies that a read miss has to be placed on the bus. When the missing block arrives, it will be in state shared as indicated here. Now we consider the case where the CPU reads a shared block. This corresponds to a read hit, so the block will stay in the shared state and no request has to be placed on the bus. Now I consider the case where the CPU tries to write an invalid block. Again, invalid means that the block is not present, so this corresponds to a write miss. A write miss will be placed on the bus, and when the block has been fetched, it will enter the state modified. Next, I consider the case where the CPU writes to a shared block. This corresponds to a write hit, but there may be other copies of this cache block which need to be invalidated. Therefore, an invalidation message is placed on the bus. After the invalidation, this cache block will be the only and most recent copy, and therefore it enters the modified state. Finally, reads and writes to a modified block. Both correspond to cache hits, and therefore no transaction has to be placed on the bus. As a side note again, the state diagram in the textbook also includes misses to shared modified blocks. Again, in my opinion, this is somewhat confusing because in that case, it's not that block that misses, but in that case, the arrow is from the victim block, the block that is replaced on a cache miss to make room for the new block. Our specification of the MSI write invalidate protocol is not yet complete. We must also provide a state diagram for bus requests. The bus requests that have been placed on the bus in response to CPU requests. This state diagram I will draw on this slide. First, if a cache controller snoops an invalidation request for a cache block that is in state shared in its cache, it must invalidate this cache block since it means that another processor wants to write this block. Similarly, if the cache controller snoops a write miss request for a block that is in state shared in its cache, it must also invalidate its copy of the block, since it means that another processor incurred a write miss and so wants to write this block. In that case, memory will return this block to the missing processor. Now consider the case where the cache controller monitors a read miss to a block that is in state shared in its cache. In this case, nothing needs to be done since the memory will return the block to the processor who wants to read it, and this copy of the block can stay in state shared. Now I consider the case where the cache controller snoops a read miss to a block that is in state modified in its cache. Since this cache has the only copy of the cache block and the memory copy is outdated or stale, the controller has to write back the block to the request as well as to memory. And the memory access needs to be aborted since otherwise the memory controller will return its stale copy of the block. Furthermore, the new state of this cache block copy should be shared, since after this transaction there will be multiple copies of the block. In this cache, the requesting cache as well as in memory. Finally, a write miss to a block that is in state shared in this cache. It means that another processor wants to write this block, but it wasn't in its cache. Again, because this cache has the only copy, it needs to write back the block to the requesting cache as well as to memory and abort the memory access. Furthermore, this copy needs to be invalidated and therefore enter state invalid. This completes the specification of the MSI write invalidate protocol. An interesting question might be, why is there no arrow labeled invalidate from the modified state? In other words, why can't the cache controller snoop an invalidation bus request for a cache block that is in state modified in its cache? Well, if we would monitor such a bus request, then our cache coherence protocol would be wrong, since it would mean that another processor had a write miss to this block in state shared in its cache, which is impossible since there is only a single copy of a cache block in state modified. Finally, an exercise to test yourself if you understood the MSI protocol. Consider the following sequence of CPU events. At time t0, thread 1 running on processor P1 writes A, then thread 2 reads A, and after that thread 3 also reads A. Finally, at time t4, thread 2 writes A. The exercise is the following. In the following table, for every time step, indicate the request that will be placed on the bus and the state of the cache block containing A in each of the 3 private caches, assuming that initially at time t0 the block containing A is invalid in each private cache. I will not provide an answer to this question, since in the next lesson, when I will discuss extensions to the basic MSI protocol, I will provide several similar examples. So you can either try to solve this question now or after watching the next video. Thank you for watching. As said, in the next lesson I will discuss extensions to the basic MSI protocol. I will also explain that while the state diagrams look relatively simple, it is actually very difficult to correctly implement cache coherence protocol. So if you are ever asked to implement a cache coherence protocol, ask for a lot of money and please donate 10% of that money to my private bank account. Hope to see you then.